Let's talk about backpropagation. So we have got this network here, x1 and x2 coming in to a layer of size 2, another layer of size 2, a layer of size 1, and finally our loss function. The activation functions are ReLUs in all of the nodes, all of the layers except the last layer where we have an ID function. ID, I just mean f of x equals x. We have weights, W1, W2, W3, W4, W5, 6, 7, and 8, W9, and W10. And then we've got biases, bias 1, bias 2, bias 3, bias 4, and bias 5 for each of our summations. So we've already looked at how to do forward propagation, how we can actually compute the loss. Now let's look at how we can compute the gradient in order to update each of the parameters. Let's pick, for instance, W9. Okay, so we want to go ahead and update this gradient. That is, we want to calculate that gradient in order to update that parameter. So what do we know? We know that the partial derivative of L with respect to W9 is equal to the partial derivative of L with respect to J times the partial derivative of J with respect to I times the partial derivative of I with respect to W9. And notice here, I'm actually just using sort of J and I to signal those values. So J is the value that's coming out of this node, which is actually y hat, right? Because this is the last layer. So the output of the last layer is y hat. So this is the same thing as the partial derivative of L with respect to y hat. And then if we look at these, that's pretty easy to do, right? We know that this one is 2 times y hat minus y. The derivative of j with respect to I, well, this function is just some g of x equals x. So g prime of x is 1, so this is 1. And then the partial derivative of I with respect to W9, well, let's just look at what I is, right? I is equal to W9 times F. So that's here, output of F times W9 plus the output of H times W10 plus R bias. Well, if we're taking the partial derivative with respect to W9, then everything else in here is a constant. The only thing that's not constant is W9. And so therefore, the derivatives of these pieces are 0, and the derivative of this term is just F. So this equals 2F times y hat minus y. Where this gets to be more interesting is when we look at some weight earlier in the network. So rather than look at W9, let's look now instead at W1. So we're trying to construct or calculate the partial derivative of L with respect to W1. Where this gets to be a bit complicated, right? For W9 it was pretty simple. We just went from L to J, J to I to W9. Great. The problem now is we need to go all the way to W1. And the problem with that is there are multiple ways to get there. So we can go L to J, J to I, up top now, I to F, F to E, E to B, B to A to W1. Or we can also take another path. So this path went up along the top. Another path goes down and then up. So it goes L, J, I, H, G, B, A to W1. So now we get two paths. Well, it turns out that because we have summations here, let's say we do a little numeric differentiation. So we take W1 and we increase it a little bit. And let's look at what happens. It increases A, right? It has no effect on C and D, but it increases A. May increase B, right, depending on whether the value was negative or positive. And then can go ahead and, depending on what these weights are, affect either E and G. Those will affect F and H. And then we'll get a weighted sum back together in here. And this will go on. So we'll end up with this weighted sum of the changes. As we go back, it turns out we can also do a sum. What we can do is do a summation of the gradient for each path. So what I'm saying is that the partial derivative of L with respect to the partial derivative of W1 is equal to the summation of the gradient for every path you can use to get there. So that will just allow us to compute the gradient along the top and then add that in to the gradient, the second path we have to get there. Let's actually just look at that. So we're going to say this equals, and let's just look at the two paths, from L to J multiplied by from J to I multiplied by from I to F, from F to E, from E to B, from B to A, and finally from A to W1. That's our first path. And then we want to add on from L to J, from I to H, so that takes us L to J, J to I to H, H to G, G to B, B to A to W1. Any individual one of these is very straightforward. In fact, we've already seen L to J, J to I. That's easy. What about, let's look at I to H. Okay, so we've already got this one and we've got this one. Let's look at I to H. So I to H, when we were doing I to W9, W9 was the variable as we were doing this partial derivative, and F was a constant. If we were taking the partial derivative from I to H, then W10 is a constant in this case, and H is the variable. So that means that the derivative is going to be W10. What about from H to G? Well, that depends. What does it depend on? It depends on whether the output of G is positive or negative. Again, if we look at the ReLU looks like a kinked line, right, like this. So therefore, if the input to ReLU is positive, the slope is 1. Whereas if the input is negative, the slope is 0. So this derivative is basically 1 if G is greater than 0, 0 otherwise. So that's the derivative of ReLU. And that's going to be the same thing as the derivative from B to A, right? So B to A is the same thing as derivative from H to G. G to B, well, by the same argument that I to H, the derivative is W10, the derivative from G to B is W6. And finally, from A to W1, again, the same argument that I to W9 was F. Here, A to W1, well, it's going to have to be X, right? Because A consists of a term x1, W1. And so when we take the derivative of that with respect to W1, the answer is x1. And if we just fill these out, kind of this is 2 times y hat minus y. This one is 1. And we get the whole sequence of these that we can multiply together. This is not how we are going to actually do the computation. And the reason for this, if we've got a deep network, let's just say we had this same size 2 layers. Okay, so we have size 2 layers and we have n layers. How many paths are there going to be, let's say from this weight, if we have n layers, all the way to the loss? Well, at each point, we can go across or we can go down, and across and down, and we have this whole network. We can go back and forth. So there are really going to be 2 to the n different paths from a weight going into the first layer to the last loss. 2 to the n sounds awfully like exponential. We do not like exponential growth in our terms, so we don't want to have an exponential number of paths that we have to calculate. That would not be very efficient, even if we have a GPU to throw at it. So we are going to look in a further lecture at a way we can use dynamic programming to reduce the number of computations we have to do. The basic idea is, gee, we're calculating the loss to I, for instance, lots and lots of times. You know, L sub j, the derivative of L with respect to J, the derivative of J with respect to I, in every one of these paths. Why don't we just calculate it once and for all and then just reuse it? That's exactly what we're going to do. We're going to be moving back through, propagating our gradient through, which is where we're going to get the term backpropagation. That's not what we want to talk about right yet, though.